Imagine every critical key in your system locked inside a dedicated, tamper-resistant vault. That's what a Luna HSM gives you. In this course, you'll learn how to connect real applications to that vault, designing, building, and troubleshooting secure cryptographic operations end-to-end. We'll move in a straight line from concepts to hands-on operations. First, you'll see how Luna HSMs are built and isolated. Then you'll connect clients, manage key lifecycles, write code with PKCS number 11, and apply crypto to real use cases. We'll wrap by testing and troubleshooting so your designs hold up under real-world conditions. Think of the course as building a secure cryptographic system from the ground up. We start with security concepts, so every later decision has a clear threat model behind it. Next, we establish connectivity, because if the HSM trust path is wrong, nothing else matters. Then we design keys and their attributes, which define what your APIs are allowed to do safely. Finally, we integrate applications and test them in production, like scenarios to validate everything end-to-end. Picture this course as 3 lanes. If you're newer to HSMs, move steadily through all sections. Those fundamentals pay off later. If you're intermediate or advanced, focus on the modules that match your projects, but keep a consistent pattern. Watch, pause to sketch the flow, try it yourself, then review any errors carefully. Before we touch any APIs or commands, we need to answer a basic question. What problem is an HSM actually solving? A hardware security module is a hardened device that generates, stores, and uses cryptographic keys, so they never leave trusted hardware. Luna HSM becomes the root of trust your databases, TLS endpoints, certificates, and signing workflows rely on. You can think of a hardware security module as a dedicated vault for your cryptographic keys. Instead of handing applications the keys themselves, you send the data in and ask the HSM to encrypt, decrypt, or sign it. The key never leaves that hardened boundary, and the HSM strictly enforces how and when each key can be used. Storing keys in regular software can work, but it assumes the entire stack stays trustworthy. The OS, file permissions, backups, even admins. Any memory dump, misconfigured folder, or compromised host can quietly expose those keys. HSMs flip that model. Keys never leave the device. Apps send operations in and get results back, but can't read raw key material. That isolation, plus strong authentication and tamper-evident logging, is what regulators and auditors actually trust. The central idea in HSM design is the security boundary. Think of it as a hardened bubble where keys are created, stored, and used, and from which they never escape in plain text. Everything inside is highly trusted. Everything outside is assumed more vulnerable. Tamper resistance protects against physical attacks, while strong authentication and role separation control who can administer versus use keys. Certifications like FIPS 140 demonstrate that this boundary meets defined assurance levels. In many enterprise systems, HSMs act as the trust anchor. They hold TLS and PKI private keys, so attackers can't steal server or CA keys. They protect code and document signing keys, so only authorized releases and records are trusted. They guard master keys for database and application encryption. They secure payment and banking keys, and they provide centralized key management with auditing and lifecycle control across the organization. Now place the HSM at the bottom of your cryptographic stack. Your application doesn't talk to it directly. It calls a crypto library to sign, decrypt, or unwrap a key. That library routes the request through an HSM client, which sends it into the secure HSM partition where keys live. PKE systems, KMS platforms, databases, and TLS gateways all follow this pattern, relying on the HSM to protect their most sensitive keys. Luna isn't a single box or service. It's a family you can deploy in different ways. Network appliances sit in your data center and serve many clients over secure channels, giving strong isolation with central control. PCIe cards live inside a server, ideal when you need ultra-low latency and tight coupling with one application. Cloud HSMs trade some direct control for elasticity and vendor-managed operations, which fits hybrid and cloud-native architectures. From the application side, treat a Luna HSM as a service that maps your needs to secure, hardware-backed operations. Need to protect private keys or a CA? The HSM keeps those keys non-exportable and performs the signing. Need to encrypt sensitive data? It runs symmetric algorithms like AES inside the appliance. And when you need high-volume TLS or transaction signing, Luna focuses on scalable cryptographic processing, so your app simply calls the APIs. At this point, think of the HSM as a remote cryptographic engine, not a key vault you browse. Your code authenticates, looks up a key by label or handle, and then sends data or a hash for operations like sign or decrypt. The key never leaves the hardware. Only results come back. Whether an operation succeeds is controlled by the key's attributes and by how both your application and the HSM client are configured. Consider your code signing key as the identity of your software. If that key lives on a build server, anyone who compromises that server can ship official malware. With a Luna HSM, the key is created inside the device, locked as non-exportable, and only used through authenticated signing requests. The build pipeline never sees the raw key, but still gets valid signatures, with audit trails showing who requested what and when. You've now seen the core idea. Keys stay inside a hardened security boundary, while applications request operations from the outside. Luna HSMs give you flexible deployment options and an API-driven model that deals in key references, not raw keys. Next, we'll dive into Luna HSM architecture and partitions and see how this model is implemented in practice.